from Sapienza University of Rome. A group of ambitious people called Sapienza Flight Team.
Sapienza Flight Team is a research project established in 2009 supported by the Department of Aerospace and Mechanical Engineering at the University of Rome La Sapienza. This year's development team is made up of 28 Bachelor and Master of Science students from various Sapienza University departments, including Mechanical and Aerospace Engineering, Physics, Electrical and Computer Engineering, Economy and Management. AENEA has been designed in order to participate to Suas 2023. It has a flight range of 15 miles at fully loaded weight, which is 37.5 pounds, thanks to a 10S2P LEVO battery propulsion pack. It's able to perform agile maneuvers with a turn radius of less than 70 feet, with a cruise speed of 22 meters per second, and to take off and land on a 250 feet runway. The UAV is capable of accomplishing a set of missions by keeping high safety and reliability levels, as well as high-precision autonomous flying. A multidisciplinary optimization approach was necessary to complete the design of the system. This was based on time and budget constraints, team experience, workforce, and available means. AENEA is a high-wing electric propeller engine aircraft, driven by a team-developed autopilot installed on an onboard computer designed and tailored specifically for the team's autopilot. The Jetson nanocomputer is used to run the artificial intelligence for the ODLC. Allowing communication between the autopilot and the artificial intelligence allow the airdrop mechanism to correctly spot and reach the ground targets with the payloads. The image acquisition setup is made up of a 5-megapixel EMX264 global shutter sensor with 12mm non-distortion lenses. This setup ensures a resolution of 10mm per pixel at the cruising altitude and a wide horizontal field of view. 120 targets in different lighting conditions and working distances have been tested to find the perfect parameters for the camera, for which a custom image acquisition script was developed. White balancing and exposure are controlled by the software to ensure dynamic color accuracy and maximum performances of the object detection system. Once a photo has been captured and geotagged with the position of acquisition, through serial communication with the flight management system, it is then processed by the object detection pipeline running on the NVIDIA Jetson Xavier. The first phase of detection is an attention layer, responsible for highlighting and cropping the areas of the image that have a higher possibility of containing objects different from the background through a combination of filters from the OpenCV2 library. The following step is the shape detection, accomplished by an object detection neural network trained on a real dataset, extended with several techniques of data augmentation. Character detection is carried out by a scene-text recognition network assembled by the team, trained on a dataset of 10,000 standard character photos. Gathering these 4 layers of information, a decision system chooses which of the recognized objects are most similar to the objective targets, and their GPS coordinates are given to the drop algorithm. The drop algorithm simulates the payload's trajectory and provides to the autopilot the necessary coordinates and orientation to land them on the correct ground targets. Payload is housed on the outer skin of the fuselage to keep unchanged the internal positioning of all the electronics. Fuselage is shaped to have 5 bottle-like indentations where the payload will be distributed and lodged, in order not to alter significantly the UAV's aerodynamics. Each bottle and appropriately sized parachute will be held in place by a net attached to the fuselage wall and to a 0-1 servo that, when the given signal is emitted, will release the net, letting the payload fall and reach the ground target. In order to predict the optimal release instant, a model was created to simulate the fall path when given outer conditions and ground target's coordinates, in order to elaborate the coordinates of the required release point. The communication system between UAV and ground control station consists of a couple of omnidirectional antennas connected with 2 RFD900X US modules that allow the exchange of telemetry data and actions on the autopilot. The ground antenna is mounted on a fixed tripod near the ground control station. The use of RFD900X US modules allow to maintain a reliable and constant data link during the entire length of the mission. Furthermore, they are FAA standards compliant. Data transmission is realized through the Mublin communication protocol. The omnidirectional antennas are characterized by a 20 dB gain, which guarantees a range up to 40 km. For safety issues, there is also a second link via Futaba 2.4 GHz protocol transmitter that connects the ground station with the drone that is activated in case of critical failures of the autopilot system. The secondary link connects a remote controller manned by the safety pilots. AENEA is a high-wing electric propeller engine aircraft. A fixed-wing airframe was chosen as the final part of a project of an academic career path based on fixed-wing aircrafts, and, moreover, the autopilot, entirely designed by the team, is based on flight dynamics mathematical model for fixed-wing aircrafts. The UAV is designed around a central carbon fiber boom and to be completely modular. Each component of the aircraft was firstly modeled using CAD softwares like SolidWorks and Autodesk, working then on the mechanical assembly. For the internal wing structure, it was decided to use a traditional model aircraft configuration of balsa wood ribs and two wing-long carbon fiber booms for bending stresses. Optimal diameters for the booms were chosen to guarantee torsional stiffness, maintaining lightness. There is also a smaller third wing boom that provides support to the wing before the aileron area. The wings are attached to the main boom with a bayonet fitting mechanism. The fuselage ribs and shelf are sandwich panels with carbon composite as skin and balsa wood for the shelf core, while for the ribs, plywood was used. The chosen manufacturing method was pressure application on the backed elements, which guarantees high quality of the final component and it's a less likely to fail process. The four fuselage ribs are all linked also by four carbon fiber beams ordered down the sandwich plate. The plate is where all the electrical components sit on. The back nose cone is also made of carbon composite, while the front nose cone is made with Kevlar composite and plaster. These elements are designed and manufactured to properly store batteries and camera inside. For the fuselage case, since the lower part will hold the payload, the structure was 3D printed using PLA as material to guarantee good load housing, stiffness, and a light structure. The upper part of the fuselage cage has no load supply, so it was opted for an extremely lightweight vinyl sheet. It was decided to use a tailwheel type landing gear that guarantees no interference with the airdrop system, easy taxi operations, and more housing room inside the fuselage. CFD simulations were used to solve the flow field with the aim of computing main aerodynamic characteristics of the drone. A simplified model was used and imported in the software ANSA by BetaCai, where a spheric domain and a computational mesh were created. To execute the fluid dynamic simulations, the chosen software was CFD++. To compute stability derivatives and control derivatives, ABL was used, an open-source software which solves, through a potential method, the aerodynamic flow around an object. Loading the geometric model and a lumped distribution mass file, it was possible to execute the trim case and the main derivatives in order to feed the autopilot. A PCB has been designed and developed to enable easy integration between the used controllers and their respective sensors. Through the printed circuit board, the Teensy 4.1 and Arduino Micro efficiently interface with the sensors, managing the information flow and allowing the autopilot to take reliable and well-informed decisions. AENEA's autopilot has been entirely implemented by the team students on MATLAB Simulink and installed on a Teensy 4.1 board. It includes a common filter for the sensor's measurements, two blocks that allow the uplink and downlink communication with the ground station via Mavlink protocol, a state flow for the switch between manual and automatic guide, managing also critical situations that require the go-home mode or the safety pilot intervention, and finally the external control loops for altitude, velocity and heading, and the internal ones for throttle and roll, pitch, yaw angles. The flight management system has 5 autonomous features. Fly by waypoints. Through the software, AENEA is able to follow a given 3D waypoint trajectory. Vectorial guidance. This mode allows the drone to follow a trajectory with previously assigned altitude, climb rate, velocity and heading, automatic takeoff and automatic landing, return to land and flight termination. The activation logic of these two modes is signal and battery dependent, as specified in the competition rules. Once engaged, the RTL mode leads the drone to the selected position, then switches to automatic or manual landing. The flight termination mode forces the aircraft in the following setup: throttle closed, full up elevator, full right rudder, full right aileron. The ground station consists of one laptop used as interface with aircraft and radio modems with their antennas. The front-end interface is Q ground control that displays the mission plan and performs telemetry and data logging. Besides, it provides setup and control functionalities and it's compatible with both TIM's software and Pixel, used as a backup system. In order to avoid any collision with objects or other UAVs, during the competition flight, the safety pilot will constantly monitor this possible situation in order to switch, in case of danger, from automatic to manual flight, avoiding in this way any collision. Among the alternatives considered regarding the autopilot, a Pixel 4 board has been configured with PX4 autopilot. This allowed to test and verify the custom-developed autopilot as a backup system. Regarding the propulsion system, the 1614 propeller has been discarded due to worse efficiency and longer runway required due to lower thrust, estimated during bench and flight tests. Besides, previously it was considered the usage of a Sony Alpha 6000 camera. The choice has ultimately preferred the current sensor because of the latter's higher color fidelity, better acquisition rate, and ease of use with software control. YOLO seemed the ideal choice for the task. However, it did not perform optimally in terms of object detection with the dataset. This led to the option of using the computer vision neural network offered by RoboFlow, which was already the team's choice for storing and expanding the dataset. Safety is essential for the entire team's success and security. To minimize or eliminate risks for team members and vehicle components, several safety constraints have been put in place, and all team members have been provided with safety courses and equipment to minimize manufacturing, process, and testing injury. One of the most critical parts of the mission that have been analyzed and tested during this year, due to the frame configuration of the aircraft, is the payload deployment. In fact, to ensure the correct parachute deployment sequence during flight and eliminate every possibility of interference with the aircraft undercarriage, a tail dragger configuration has been chosen as compared to the tricycle gear. Different aircraft designs have been examined, and to avoid delays during the testing campaign in case of components failure or accident, multiple backup instances of every component have been manufactured thanks to detailed economic and working planning in advance. After training on the provided augmented dataset, the neural network has achieved a good accuracy, both in detection and classification. First land tests have been performed to test the dropping mechanism and parachute performance. Then manual drops have been accomplished while flying to test the accuracy of the fall path prediction. Given the good precision of the fall prediction model, the attention focused on autonomous air drops performed by the autopilot, with all calculations performed on the Jetson. All the tests for the RFD900X module's performances were made in a suitable location, far from buildings and signal interferences. The used evaluation metrics are the RSSI, Received Signal Strength Indicator, and the number of received packets. Both of them can be measured using the RFD tool software. Different trials have been made with different values of data rates, transmitted power for the local radio, and distances. After more than 10 cumulative flight hours, it's possible to affirm that the UAV is safely capable of satisfying all requirements for flight performances demanded by the Suas rules. It has also been tested in either manual or autonomous with extremely high wind conditions with good results. To tune and safely test the autopilot control loops and modes, a parallel Simulink model dedicated to the software-in-the-loop simulation was developed. This includes a sophisticated mathematical model of the aircraft, blocks that simulate the sensor's output, including noises, blocks that simulate the actuator's action, aerodynamic surfaces and throttle, the autopilot itself. It is possible to simulate all 5 flight conditions foreseen by the autopilot. In particular, for the autonomous flight, the software-in-the-loop simulation allows to set the desired waypoints in the startup file, together with all the parameters of the whole Simulink model. At the end of the simulation run, it is possible to display the path followed by the aircraft along the waypoints, and several simulations have been carried out entering waypoints inside the airfield in order to foresee AENEA's real behavior and to understand which order of distances it is able to manage. The autopilot was tested in real time for 30 flights for a total of 5 hours. All tests regard autonomous flight with waypoint navigation and automatic takeoff and landing. The flight stability was tested by missions that were planned from the ground station by imposing the desired waypoints via key-ground control, and the flight turned out to be in accordance with the software-in-the-loop simulation. In order to furtherly verify the developed autopilot, the same missions were carried out also using Pixoak. The obstacle avoidance is carried out in manual flight. During the tests, the safety pilot has switched from automatic to manual flight to perform a possible maneuver in order to avoid a collision, with 100% success. To ensure a perfect mission result, 14 full missions have been tested with encouraging results, showing that the competition members are gaining experience and coordination with time. Team captain starts a 10 minutes configuration timer, and every competition member initiates during his assigned procedures following an accurate checklist. Once the setup is terminated and after the pre-mission brief, the aircraft is carried to the runway and the ground control station operator, coordinating using an handheld transceiver, the safety pilot, gives the takeoff command. After the mission, the aircraft returns to the tent in order to begin the tear-down procedures.